What is up, everybody? It is Mr. Boylan, and today, what in the heck are we gonna do in this video? We are going to use bond polarity and molecular geometry to explain how to predict molecular polarity. Okay, so first thing we want to do is determine whether or not a bond is polar or nonpolar, and then we're going to determine whether the orientation of the bonds, using our infinite knowledge of molecular geometry, will result in a net dipole or zero dipole. Sounds confusing, but basically all we want to know is, will a molecule overall have a partially negative region and a partially positive region? Will it have a dipole or not? Now, if a molecule is polar, it is said to have a net dipole because they have an uneven charge distribution. One of those atoms is hogging the electrons, and a dipole is then created overall by equal but opposite charges that are separated by a short distance. So, as you take a look at your notes, a classic example of a polar molecule overall, or a molecule that has a net dipole. Recognize that chlorine, the more electronegative atom, is going to hog those electrons, creating partially positive and partially negative regions in the molecule. Now, it turns out there are actually two things that you need to look for in order to determine whether a molecule overall is going to have a net dipole. First, it must have polar bonds. And second, it has to have an asymmetrical shape. So, as you take a look at your notes or the image on the screen there, let's start with carbon dioxide. Carbon dioxide has two polar bonds, but the oxygens are pulling in opposite directions, effectively canceling one another out. So, overall, there is no net dipole. I like to think of it as a tug of war, and the opponents on either side are equally matched. And so although they are both vying to pull those electrons towards themselves, the opposing oxygen is pulling back with equal strength, effectively canceling out the dipoles for the molecule overall. Recognize, though, in a molecule of water, we have not only polar bonds, but due to the asymmetrical orientation of the molecule, there is going to be a net dipole overall. And notice in your image that net overall dipole is oriented so that the negative end is up near the oxygen, the positive end is down near the hydrogen. Now, generally, it's lone pairs on the central atom that will create a polar molecule overall, and there will generally be a strong pull in the direction of the lone pairs. So, take a look at ammonia, a classic example of a polar molecule. Again, the lone pair on the central atom is a great indication that we are going to have a polar molecule overall. Water, of course, being another fantastic example. And once again, we've got a couple of lone pairs on our central atom. So you want to be looking out for lone pairs on that central atom when you're trying to determine whether or not a molecule overall will be polar. However, recognize that there are still some polar molecules even if there are no lone pairs on that central atom. The molecule can still be polar overall if the atoms bonded to that central atom are different. So take a look at the two molecules on your screen. In CH2Cl2, there will be an overall net dipole in the direction of those chlorine atoms because the chlorines can pull more strongly than the hydrogens can, creating a slightly negative region by those atoms. In a molecule of CH4, because each of the atoms are pulling in equal strength, there is effectively no net dipole. And last thing to keep in mind, it is molecular polarity that affects what are called the intermolecular forces of attraction, which we'll learn about in an upcoming video. But basically, recognize that when you have molecules that have slightly negative and slightly positive regions, that's going to cause some attractions in between molecules. All right, and that brings us to an end for this video. Have a fantastic day.